In the following lecture, we're going to try and solve October-November 2017 question paper 5.2, and we're going to try, this is the planning, analysis and evaluation paper, and we're going to try and solve the first question of this paper. So the question reads that verdigris is a green pigment that contains both copper 2 carbonate and copper carbonate, which is given, the formula is given, and copper 2 hydroxide, and the formula for copper 2 hydroxide is also given in varying amounts. Both copper compounds react with dilute hydrochloric acid. So both of them are shown, copper carbonate reacting with HCl to produce copper chloride, carbon dioxide and water, and the same copper hydroxide acting as a base reacts with an acid to produce salt and a water molecule. Now, the first question is about planning, and you're being asked, you are to plan an experiment to determine the percentage of copper 2 carbonate in a sample of verdigris. Your method should involve the reaction of verdigris with dilute hydrochloric acid, and you're provided with the following materials. So let's figure out what we are trying to plan over here first. So this over here is verdigris, copper carbonate and copper hydroxide. It's a combination, varying amounts. So we are not sure what amount of copper carbonate is present, and you're being asked to figure out the percentage of copper carbonate in a particular sample of verdigris. Now, to plan the experiment, you're also provided with some of the materials. The materials that you have at your disposal are, you're provided with the following materials. You have 0.5 grams of a sample of verdigris, this entire thing, it's a mixture. And you're given 10 mole per dm cube of hydrochloric acid, which is HCl, and commonly available laboratory reagents and equipment. So the available apparatus that's already present in the lab, that's with you. And you may assume that any other material present in verdigris is unaffected by heating and is not acidic or basic. So what this statement actually means is that there must be other impurities also involved, and he's told us two things about those other impurities. So for example, you have 0.5 grams of verdigris, so there would be some amount of copper carbonate, some amount of copper hydroxide, and some other amount of impurities. And he's told us that the impurities are unaffected by heating. So when you heat the verdigris, the impurities are going to remain unaffected. Nothing happens to them. And they're neither acidic nor basic. So when you react verdigris with acids or bases, it's these compounds that are going to play a role or not. But the impurities are not going to do anything. So let's move on. Not much there. Part one of the question is, explain why a titration would not be a suitable method to determine the percentage of copper 2 carbonate in a sample of verdigris. So the question states, why not just pour HCl and do titration and make verdigris, which contains copper carbonate and copper hydroxide, to react with HCl. Now the problem is that as it's already shown with the equations over here, that both copper carbonate and copper hydroxides, they both react with HCl. So if they're both reacting with HCl, so how would you figure out, even if you figure out the moles of HCl, you won't be able to figure out how much of that HCl reacted with copper hydroxide or whether it reacted with copper carbonate. So HCl is going to react with both of them. So your best option would be to have a reagent that only reacts with copper carbonate and not with copper hydroxide, so you can figure out the amount of copper carbonate in verdigris. So I'm going to write the answer now. So HCl reacts with both copper carbonate and copper hydroxide as they are both basic. It's a 1 mark question, so not a lot of detail is required. No further explanation should be required for that question. Let's move to part 2 of the question, which is that 10 mole per dm cube HCl is corrosive and too concentrated for use in the experiment. Describe how you would accurately prepare a 250 cm cube of 0.5 mole per dm cube hydrochloric acid from the 10 mole per dm cube HCl provided. Now this is an extremely concentrated solution, and you're basically your aim is to dilute it. Include details of any apparatus, including the capacities in cm cube you would use. Now this is a 2 mark question. So again, 2 marks, not a lot of detail, although you can go into a lot of detail with this question. But again, because it's only 2 marks, don't go into too much detail. You don't even have that many lines. So the first step is focus on the solution that you're trying to prepare. Solutions are always prepared in volumetric flasks. So here you can see the volumetric flask, which only has 1 mark, which usually is the 250 cm cube mark. So this is solution. The first thing is figure out how many moles of HCl do you require to actually make this solution. So the volume is given and the concentration is given. So moles is concentration multiplied by volume. So we're going to do just that. So the concentration provided is 0.5 and the volume that's provided is 250 cm cube, which should be converted into decimeter cube. And the answer that I'm getting is 0.125 moles of HCl that are needed. Now the next part is, where do you get these moles? So remember, your original solution is a 10 mole per dm cube HCl. It's a very concentrated solution. So you're going to use a burette and you're going to use this burette to put in a certain amount of HCl into this flask over here. These are the moles that you require to make this solution over here. And all those moles are supposed to come from this very, very concentrated solution. So let's now figure out for this very concentrated solution what volume is required. Now again, we're going to use N is equal to C into V. Now remember, this is, I'm doing this for the very concentrated solution. These are the moles that my targets are. I need these many moles in this flask over here. So I'm going to use this HCl. The moles I already know. I need 0.125 moles of HCl. The concentration of this very concentrated HCl from which I'm going to get these many moles is 10 mole per dm cube. So that's 10 mole per dm cube and multiplied by the volume, which is right now unknown. So let's figure this out. It would be 0.125 and divide by 10, and this would be my volume in decimeter cube. And if I convert this volume to cm cube, this would be equal to 12.5 centimeter cube. So that's the first thing that I'm going to do. So 2-mark question. The first thing is, I'm going to pour in 12.5 cm cube of HCl from this very concentrated solution into this flask over here. So that part has been written over here. This is my answer now. Add 12.5 cm cube of 10 mole per dm cube of HCl into a volumetric flask by using a burette. And I could have, the burette is very accurate. Remember, accuracy is very important. Now next step is, once that HCl, these many moles of HCl are in there, this has to be a 250 cm cube solution, because that was the volume of the solution. So what are you going to do? You're going to pour in distilled water into this flask and make it up to the 250 cm cube mark. So that is the next step. And remember to use the word distilled water. So the next step is fill the volumetric flask. So fill the volumetric flask by adding distilled water up to the 250 cm cube mark, and your solution would be prepared now. So 2 steps involved. The first thing was to calculate the amount of moles that you need to make this solution of HCl. You needed 0.125 moles. Where would those moles come from? Because this was your original solution, so those moles are going to come from this very, very concentrated solution. So we figured out the volume of that solution that was required to give us these many moles, and then you fill it up with water, distilled water. Remember, don't write water alone. And once you fill it up, it's going to become a 250 cm cube solution containing that many moles. So the concentration would be the required concentration as well. Let's now move to part 3 of the question, which says that identify a dependent variable that you could measure to determine the percentage of copper to carbonate in verdigris. Your answer should be based on a difference that you can identify between the reaction of copper to carbonate and copper to hydroxide with excess hydrochloric acid. Now, if we go back and have a look at the original reaction that was going on, where verdigris was reacting with HCl. Now everything looks exactly the same salt being produced, the same water molecule being produced, but since you're measuring the percentage of copper carbonate, there's one thing that will tell you the amount of copper carbonate, and that is carbon dioxide gas that's being produced, because even though copper hydroxide is reacting with HCl, but it's not producing carbon dioxide gas. So all the carbon dioxide gas is actually coming from copper carbonate. So if we focus and measure. Remember, the dependent variable is the variable that is dependent on the changes that you're making. For example, it's dependent on the percentage of copper carbonate. If there's more percentage of copper carbonate, then the volume of carbon dioxide that is produced would depend on this independent variable. So this is the variable that we are trying to figure out, and this is the variable that's dependent on it. So carbon dioxide is going to be the key in figuring out the percentage of copper carbonate. You figure out the moles of carbon dioxide, you figure out the moles of copper carbonate in Verdigris. So I've written down my answer. Identify a dependent variable that you could measure to determine the percentage of copper to carbonate, and that is going to be the measure. I'm going to measure the volume of carbon dioxide that's being produced. So again, it's 1 mark question. Let's move to the next part of the question, which says, draw a diagram to show how you would set up the apparatus and chemicals to measure the dependent variable identified in 3 and label your diagram. Now here's the apparatus that I have drawn, where I have a conical flask. Reason I'm using a conical flask is because of its smaller opening, and you can, this is also known as a sidearm flask because it's specifically designed for collecting gases. Normal conical flasks could also be used with a tube attached to the rubber bung and sealed properly. Here's my gas syringe, and I'm going to try and collect carbon dioxide gas that's going to be released when verdigris, which I've kept in this tiny tube, or you can say that this is my small reagent bottle. Reason being that I can't open the top of this container and then add verdigris into HCl, because if I add that, then air would enter. So I want the apparatus to be ready, and if I pull on this thread over here, this verdigris, which is in this tube over here, would start reacting with the HCl. It's going to tip over, and it's going to start reacting with the HCl that's in the flask already. So this is one way that I can add verdigris and mix it with the HCl without opening the tap, so no gases enter or leave the flask. So all the carbon dioxide that's going to be produced ends up going into the gas syringe, and there's the very little loss of air, because otherwise I would have to open it and quickly shut it and then add verdigris, and some air might, and that would lead to some sort of error in the final volume of carbon dioxide that's collected. Now let's move to the next part of the next page, which says, use the axis below and sketch a graph to show how the dependent variable you identified would change during your experiment. Extend the graph beyond the point at which the reaction is complete and label both axes. So this axis is my independent variable, and this axis is my dependent variable. So here are the two axes that I've labeled. Volume of carbon dioxide, that was my independent variable, that was what I was trying to collect. And on this axis I have time in seconds. This time over here would represent duration. So let's quickly sketch how the carbon dioxide is going to be produced. If you look at the experiment and go back and have a look, initially, remember, all reactions behave in a similar way, that initially carbon dioxide is going to be produced at a very fast pace. And then after some time, the verdigris would have reacted, and the amount of carbon dioxide that's being produced would stop, and the amount of carbon dioxide would become constant. So initially, the volume would increase very fast, and then it slows down as verdigris ends up finishing, and it ends up reacting with HCl. So the graph would have a shape similar to this. A very steep rise, which means volume of carbon dioxide is being produced at a very fast pace, and then it becomes almost constant as the reaction stops. Now the last part 6 of the question states that the student carries out the experiment once. Describe how this one experiment should be carried out to ensure that the results are as accurate as possible. Now firstly, one experiment is definitely not recommended because of the random errors that could be present. Doing multiple experiments and then taking out the average reduces the error, especially the random error. Now, how would you do just one experiment and do it as accurately as possible? So it's a 1 mark question, and any reasonable attempt at answering how you could improve accuracy would be good enough. So if you look at the apparatus over here, I'm going to make a few things. How could you improve? Now look at the apparatus as carefully as possible, because you've already done a few things. Using this thread was very intelligent. It would make the experiment, the output or the volume of gas that is collected, it would make it very accurate. Now one thing is you could check the seals. There's no gas leakage. That's one way. So that's one suggestion. Check the gas. Remember, whenever you're dealing with gases and you're trying to measure the volume of gas, that's one thing that you're going to try and do. Check the gas leakages as carefully as possible. Another thing that could be done is you could improve accuracy by controlling other variables which are not involved in this experiment. The other variables could be many different variables. There could be variables related to pressure. So for example, although we don't think the pressure is going to fluctuate that much, but temperature changes are also going to vary. The amount of carbon dioxide, because gases, they expand when temperature changes. So you could ensure that the temperature remains constant. Another way to improve the accuracy is to get a more accurate syringe, or because you're going to be measuring the volume of verdigris or the mass of verdigris, you could use more accurate apparatus as well. So many different suggestions for improving accuracy if you're doing only one experiment. But again, I repeat, one experiment is definitely not recommended. So let's, although it's a 1-mark question, let's write several suggestions for answering this question. So here are my suggestions. Check that apparatus is sealed properly, no leakages. Use thermometer to constantly monitor the room temperature and ensure that the room temperature is stable. There are no fluctuations because it's going to affect the volume of carbon dioxide that you're collecting. Improve accuracy of the apparatus, more accurate mass measurements, more accurate syringe. For example, a 2 decimal place syringe, that would give you even more accurate results. Now the next part of the question, part 7, states that a student suspected that a 0.5 gram sample of verdigris only contained copper carbonate. So there was no copper hydroxide present. Calculate the minimum volume in cm cube of 0.5 mole per dm cube HCl that would be needed for the complete reaction of the sample if the student was correct. So it's a simple moles question, and it only contained, now the question states that the student is suspecting that verdigris only contained copper carbonate, 0.5 gram. So I'm going to start with 0.5 gram copper carbonate and try to figure out the moles of that copper carbonate. So let's find the moles of copper carbonate, and moles is mass divided by MR. The MR is already provided, that's 123.5. And this provides me, the moles that I'm going to get is 4.05 times 10 to the power minus 3 moles of CuCO3. Now if you look at the reaction that was between copper carbonate and HCl, let's go back. So over here you can see the reaction copper carbonate with HCl. The stoichiometric relationship was 1:2, which means the moles of copper carbonate, the moles of HCl are going to be twice that amount. So the moles of HCl are going to be double the amount of moles, which is going to give me, if you double this, so we're going to try and double this on our calculator, it's going to give me 8.10 times 10 to the power minus 3 moles. Now remember to try and keep your values to 3 significant figures. So you're getting 8.10 times 10 to the power minus 3 moles. And using this, I know the concentration of HCl. So we're going to use the formula moles is equal to concentration multiplied by volume. The moles that we need for HCl, the minimum moles that are required for it to react with copper carbonate, that's 8.1 times 10 to the power minus 3. The concentration is known as 0.5 mole per dm cube into V. And I'm going to try and solve for V now. And the answer that I'm going to get is if I divide this by this, I'm going to get 0.0162 dm cube on my calculator, which if I convert that into cm cube and I multiply it by 1000, it's going to give me 16.2 cm cube. Now the next part of the question, part B of the question states that the following information gives some of the hazards associated with the chemicals used in the procedure. So there's copper 2 hydroxide, and the hazards that are associated with it are that solid is classified as a health hazard and is harmful if swallowed. Dispose of by reacting no more than 60 gram in 1 dm cube of warm, 1 mole per dm cube ethanoic acid before. So they're basically saying that reacted with ethanoic acid and then pour it off. Otherwise, swallowing it is harmful. So copper carbonate is a harmful substance if swallowed and has to be disposed of carefully. Hydrochloric acid solutions equal to or more concentrated than 6 are classified as corrosive. So 6.5 mole per dm cube is highly corrosive. And then solutions equal to or more concentrated than 2.7 mole per dm cube but less concentrated than 6.5 are classified as moderate hazard and are irritant. So 2.7 mole per dm cube and above, they are going to irritate you, but they're not very corrosive. Beyond 6.5, they are very, very corrosive. So again, a 1 mark question. Describe one relevant precaution other than eye protection and a lab coat that should be taken to keep the risk associated with the chemicals to a minimum. Explain your answer. So the three precautions. You can use gloves, wash hands, mainly because it's corrosive. So that's because you have to explain your answer as well. Or you could have written face mask. Reason face mask would be helpful is that it's harmful. Copper carbonate is harmful if swallowed. So you never know that some small tiny piece of copper carbonate can get swallowed. So better to use a face mask. Any of these answers would have been suitable and correct, would be deemed correct. And they just required normal common sense to figure this out.